Imagine you're visiting a foreign country you've never been to before. Your new hosts have all kinds of customs that you don't understand. One time you look an elderly woman in the eye and she scolds you. Another time you wander into a building with all sorts of strange ornaments and you're escorted out by an angry group of locals. You mean well, but you simply don't know what these people care about. You don't know their utility function, and that makes you want to be careful. Only once you've learned the local customs will you be able to act freely. This kind of moral uncertainty might be something we want our AI systems to have. One way this might be achieved is by giving an agent a probability distribution over utility functions and a method for updating. The agent could then use its observations and its intelligence to find the best possible utility function in the set. But this only works if the set of utility functions and the updating rule are correctly specified. So now we have a question of obedience. The AI starts off not knowing much about its utility function, so we want it to learn from its human supervisors. But the supervisors aren't completely sure of their utility function either. If we knew for sure what our utility function was, we could just program that in and we wouldn't need the learning process. So we have some questions. How do we make the system learn? When should it be obedient? And how do we make it obedient? A toy model of this is the off-switch game. You have a human and a robot, and there's a button that the human can press to shut down the robot. The robot decides on an action that it thinks would be good, something like pick up that box or knock over that priceless vase or whatever. We'll call this action lowercase a. So the robot has a choice. One thing it could do is wait for human feedback. If it does that, then now the human supervisor has a choice. Either choose to allow the robot to take action A, or choose to press the shutdown button. Or, instead of waiting for human feedback on action A, the robot can simply take the action. The final option available is the robot can shut itself down. So let's put the utilities in. If the robot chooses to simply do A, it gets the utility of action A. So either if it simply does the action itself, or it waits for the human and then the human allows the action, you get this utility. On the other hand, if the robot is shut down, it's finished, so it gets utility 0. So the robot can choose either to be obedient and wait for the human, or be disobedient and just do the action anyway or shut itself down. We want to calculate the incentive for obedience, which we'll call delta. The incentive for an option is just the difference in utility between that option and the alternative. So in this case, the incentive for obedience is equal to the expected utility of being obedient minus the expected utility of being disobedient. But to calculate the robot's expected utility for obediently deferring to the human, we need to know something about how the human is going to make this decision. Presumably, the human is more likely to allow the action A if the utility of that action is high. So let's define a function which we'll call big A. We'll define it properly later, which is the probability that the human will allow an action of a certain utility. So the incentive for obedience, delta, is equal to the expected utility of obedience, which is this subtree here. So that will be the probability that the human will allow an action with the utility of A times by the utility of A. That is to say, the utility you get for A happening multiplied by the probability that A is allowed to happen. So all of that minus the expected utility of disobedience, which in this case is whichever one is bigger, the utility of A, or the utility of shutdown, which is 0. But the point is that the robot is uncertain about the utility function. So let's define that. Rather than the robot knowing for sure that the utility of action A is exactly U sub A, maybe it has a normal distribution, centered at A, and with a standard deviation of sigma. So sigma is a measure of the robot's uncertainty. And it turns out that the larger sigma is, the greater the uncertainty is, the greater is the robot's incentive to defer to the human and be obedient, which makes sense. So, do we want the robot to always be obedient? Well, only if the human is rational. For example, if the robot is driving a toddler down the motorway at 70 miles an hour, and the toddler decides it should shut the robot down, maybe we would want it to not be obedient to that command. So, the agent can model the human's rationality or irrationality, and then decide whether they should obey or not. Let's call the supervisor's level of irrationality beta, and make it another argument to our allowance function. We'll define a new version of the allowance function. The probability that the supervisor will allow a particular action to take place now depends on the utility of that action and how rational the supervisor is. Here's how we define that function. So here's how this works. Our new variable, beta, has a Boltzmann distribution between 0 and infinity. So suppose beta is 0. This represents no irrationality, a perfectly rational supervisor. So how does this work then in the case where beta is 0, so we have a perfectly rational supervisor, and the utility of action A is positive? Well, we end up with a positive number divided by 0, which is infinity. So e to the minus infinity is 0, so we end up with 1 over 1, a probability of 1. In other words, a perfectly rational supervisor will allow an action with positive utility with probability 1. Now suppose the utility of action A is negative. In that case, this negative number divided by 0 becomes negative infinity. So e to the minus negative infinity is e to the infinity. So this whole bottom term becomes infinity. 1 over infinity is 0. So a perfectly rational supervisor allows actions with negative utility with probability 0. On the other hand, suppose that beta is very large. Suppose beta is infinity, a perfectly irrational supervisor. In that case, it doesn't matter if the utility of A is positive or negative. This term becomes 0 because you're dividing by infinity. E to the 0 is 1, so this becomes 1 over 1 plus 1, in other words, 1/2. So with beta of infinity, with a perfectly irrational supervisor, regardless of what the utility of the action is, it will allow it with 50% probability. It's completely random. And of course, for every value of beta in between 0 and infinity, there's a variation there. The higher beta becomes, the less the agent's allowance of the action is determined by the utility of the action, and the more it becomes just random. And it turns out that if we take our new allowance function and we plug it in place of the old one in our expression for the incentive for obedience, we find that the more rational the supervisor is, in other words, the smaller beta is, the more the incentive for obedience, delta. There is, however, one problem. Practically speaking, the robot has to observe the actions of their supervisor and learn two things about them: their utility function and their level of rationality. The problem is, you can't learn either of those without some knowledge of the other one. To learn someone's utility function by observing their actions, you need to know something about how their actions relate to their utility function, which depends on their rationality. And in order to learn someone's level of rationality by observing their actions, you need to keep track of how often they make good decisions versus how often they make mistakes. And unless you know something about their utility function, you can't tell the difference between good decisions and mistakes. So this is an open problem.